Okay, folks, let's take a look at number 7. See if I can get this out of your way. All right, so we got a physics student heading down a slope from rest with a constant acceleration. Well-labeled diagram, okay. Right, so acceleration is down the slope. This is 28 degrees. Great, so there's a force diagrams. Okay, so what I know is there's a force normal on skier by surface. There's FG on skier by earth. Is there a coefficient of friction? Yeah, so they're talking about coefficient of friction, so we know there must be some friction, right, on skier by surface also. Okay, great. So you'll remember that we talked in class about how sometimes it might be easier if you have something that's like this to actually put the incline in so you can see it. Sorry, that was bad. Back it up. Okay, let's see if I can make it more matching. Oh, anyway, if you can kind of put it in. Oh, that was kind of good there. All right, so now that the incline's in, you can sort of see where things need to go, maybe just a little bit better. So now I can drop this FG here. I'll just try to remind you of a few things about inclines. It's always better if you can put the FG over here on the close to theta. Then we still need to have the same forces that we had on the other diagram, right? So we don't lose any, but when we're doing the components, then we can actually put the components in. So I think I'll just make this blue. So there's the FG perpendicular, which is mg. So this theta is this theta. I'll just remind you of a couple of things, okay? I'll do the parallel to the plane in pink. So this would be FG parallel. So here's what I would remind you. There are a couple of things. First of all, you can look at these as similar triangles. So this triangle with a right angle here and theta here and some angle there could be the same as this triangle with a right angle here. And if you can imagine that this angle is this one right here, if you kind of flip that up, then this is theta. The way I usually think about it is that if I look at this triangle right here, there's a right angle there, theta is here, and this is some other angle. I'll say alpha. Alternate interior angles are equal, so there's an alpha. I know this is a right angle, so that only leaves this to be theta. So I don't need you to prove that that theta is, let me get rid of some of this extra drawing stuff, that those thetas are the same, but I do need you to know it. Those thetas are the same. So what that means is that FG perpendicular is mg cosine theta, right, because it's adjacent, and FG parallel is mg sine theta because it's opposite. So if I'm just going to write down my given, right, what do I have? Theta equals 28 degrees. Is it 28? Yeah, great. What do I have? Acceleration equals 2 meters per second squared. Time equals 15 seconds. FG equals what? 800? Yeah. FG parallel equals 800 sine 28, which equals 376 newtons. FG perpendicular equals 800 cosine 28, which equals 706 newtons. If I were going to do a really good job, I would say what FG perpendicular equals 706, right? And FG parallel equals 376. Okay, so there's that. All right, so we've got a well-labeled diagram. We've done a force diagram. We haven't done a graph. So let's see, starts from rest. So there we are. I'm sort of liking the 10, 20, 30, 40 here. Oop, 10, so bad. 10, 20, 30, 40. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so something like that. I'm going to go from, for 15 seconds, right? So about right here. So I'm going to have an acceleration of 2 for 15 seconds. So if I kind of work that out, looking at what's happening, it's going to take me to about there for 15 seconds, right? So that'll be about, so the slope has to be 2. So I just have to draw it in such a way that the slope is 2. Then I could know that the area under is going to equal the distance covered, right? And it's going to equal 1/2 base times height, which in this case would be, let's see, the base is, what do we say, 15? 1/2, 15. And the height is 30. So hopefully that comes out to be close to 225 meters. Okay. So I don't know if they even ask about that, but who cares? But we did do the graph, so yes. Yes. The length of the slope. List given quantities to determine the length of the slope. Well, that's kind of a weird question. To me, I think they're asking how far did it cover, but I really, as an AP reader, I can tell you that I do not think they would ask it that way, because even though he starts from rest, you don't know if he starts on the top of the slope, and I certainly didn't draw it that way. So I don't like that wording. Again, they're just asking total displacement, right? So, which is what we found. So we're going to say, hey, we've got that. So now we just need coefficient of friction. So I'm inclined to say sum of F equals MA, right? In the X direction, it's going to be FG parallel. Now I notice that I really didn't do my equality statement, which is kind of crappy, equals MA. And what do they want? Coefficient of friction. So I know this number because I already found it, didn't I? Yeah, so 376 newtons minus mu, and force normal is the same as force perpendicular, so that's 706 newtons, right, equals mass, which is 80 kilograms, times acceleration, which is 2 meters per second squared. So let's see, 376 newtons minus what's 160 newtons equals mu times 706 newtons. And then I think if I subtract here and divide by 706, the mu should be 0.3. All right, I think we are out of here on number 7. Closer to tip